Uh, is this wave optics?
Am I audible?
Yes, sir.
Okay. So, in the last lecture, we have finished electromagnetic waves. So, we'll start optics today. So, optics, we divide optics into two parts. One is wave optics, another is ray optics. Wave optics is particularly chapter number 9 of NCRT, and ray optics is in 10th chapter. So, in wave optics, these are the chapters that you will study: Heinz principle, interference, diffraction, polarization is deleted, Doppler's effect is deleted. Also, a major portion of diffraction is also deleted from your syllabus. And this Heinz principle is a very small topic, like it's a one lecture topic, it's a very theoretical thing. The major topic, which is there in your syllabus in wave optics, is interference. That's the major topic. Diffraction is a very minor topic, one lecture, hardly it will take one lecture. Polarization and Doppler's effect are not in your syllabus. So this starts with the concepts of wave and particle. So whatever you have around yourself, you can divide them into two categories. It can be a particle or a wave. This pen that I am taking is a particle. Sound, you can divide sound as a wave. We will study de Broglie hypothesis, so I'm not coming to that dual concept. But when you consider light, light shows both particle as well as wave characteristic. There are certain experimental results which shows that light is a wave. That is interference, diffraction, polarization, Doppler's effect. These phenomena are usually wave phenomena. So light shows interference, it shows diffraction, it shows polarization as well as Doppler's effect. So from these experiments, one can conclude that light is a wave. On the other hand, light supports some other experimental results like photoelectric effect, which shows that light consists of stream of particles. You can divide light. So light shows wave as well as particle characteristics. So when we study the wave characteristics, we have wave optics. So I'm not going
Sir,
into
can you repeat?
yes. See, light shows both the wave as well as particle characteristics. So these experimental results like interference, diffraction, polarization, Doppler's effect, these shows the wave characteristics of light. And this photoelectric effect shows the particle characteristics of light. So currently we are doing wave optics. We'll be discussing these phenomena. So in wave optics, we have these 5 chapters. Out of this, the fourth and fifth are not in your part of syllabus now. Only 3 are there. Please note it down. Then we'll start with the first chapter, Heinz principle. That's wave optics, chapter number 9.
So we will start with the ray optics.
Wave.
Wave optics.
We'll first do wave optics, then we'll do ray optics.
So 1 minute, can you scroll up? Then see.
Okay. So these are the topics in wave optics. Yes, can I scroll up? Okay, so let's start with the first topic of wave optics, which is Heinz principle. So Heinz gave the first theory for the propagation of light in the form of wave. Before Heinz theory, it was believed that light consists of stream of particles. Basically, there was a theory given by Newton, which is known as corpuscular theory. In corpuscular theory, Newton said that light consists of stream of particles, and those particles are moving. So light is basically particles. It have particle nature. Heinz was the first guy who proposed the wave theory of light. Heinz says that no, light is not a stream of particle. Light is a wave basically. Now, when Heinz proposed that light is a wave, then the next question was, okay, if light is a wave, then how does that wave propagate? So to explain the propagation of light, Heinz gave a theory which is known as Heinz principle, which is based on the concept of wavefront. The whole of Heinz theory is based on a single concept, which is the concept of wavefront. So to understand the concept of wavefront, let's take this example first. See, we have to study light waves, not water waves. But to understand the concept of wavefront, this is a very good example of water wave. See, this is the surface of water. Initially, this surface was calm, no disturbance in this surface. You drop a stone here. When you drop a stone, this stone acts as a source of disturbance for this water surface. And what this stone did, this stone generates some disturbance. So this stone generates this first set of disturbance. Then these disturbances generated the next set of disturbance. Then these disturbance generate the next set of disturbance. And this is how the disturbance that was initially generated by a stone travels from one point to another. Heinz called these disturbances as wavefront. So if you take these circles, you can consider these circles as the wavefront. But these are the wavefronts for the the waves which are getting generated on the surface of water. So these are wavefronts for water waves. But we don't have to, we are not studying water waves here, we'll be studying light waves. But same concept can be applied to the light waves also. So I'm repeating again. To understand this concept of wavefront, the best example is to understand wavefront in context with water wave. So this is the water surface, calm surface. There is no disturbance here. You dropped a stone here. This stone act as a source. You can say this is the source of disturbance. This disturbance generate first set of disturbance, which is known as wavefront. Then it generates second set of disturbance, second wavefront. Then this wavefront generate next wavefront. And in the form of wavefront, your light waves travels from one point to another. So when we use Heinz theory, we say that light is traveling in the form of wavefront. Now, how to define a wavefront? Wavefront is the locus of points. Locus of point means wavefront is the collection of points which are at a fixed distance from a certain point, and that certain point is source. Like if you take a source and you take some points at a fixed distance from this source, and when you connect all these points, the shape that you get is your wavefront. So what is wavefront? Is the definition of wavefront. It is continuous locus of points which are vibrating in same phase. Same phase is also important. To understand phase, you can take this example of water wave. So when water particles are vibrating, if you take this circle, this outer circle, these are water particles here. The water particles are vibrating in two modes. Some are coming in outwards direction and some must be going into the inwards direction. So all particles which are coming outwards are in same phase and those which are going inwards are in same phase. So to draw wavefront, we take only those particles which are in same phase. Means if I take example of water wave, then I take only those particles which are coming either outwards or they are going inwards. So to draw wavefront, we have two conditions. First is all points on the wavefront will be at a fixed separation from the source. So if you take a source and you take points on the fixed separation, then the shape would be spherical because this is what we do in 3D. So if you have a source and I ask you to draw the wavefront for this source, what you will do, you will take points and these points will form a sphere and the wavefront will be spherical. So when you use Heinz theory, you say that, okay, light waves travels in the form of wavefront. So if I say this is my example of wavefront, this is my wavefront. Now after wavefront, if you want to draw rays, what we do, we draw perpendicular on the wavefront. So all perpendicular on the wavefront will represent ray. So this is a sphere. I'm drawing normal on the surface of sphere. To draw normal on the surface of sphere, what we do is we take radial directions. All radius are perpendicular to the wavefront. So these are the radial directions. All these radius are perpendicular to the wavefront. And these radial directions represent rays. So I'm repeating again, if you have a wavefront and you want to draw a ray, what you will do, you will draw perpendicular on the wavefront. Perpendicular on the wavefront are rays.
Sir, they are coming like outwards.
Yeah, they're coming outwards. And remember, light energy travels in the direction of ray. So this is the concept of wavefront. Is it clear what is a wavefront actually? Anshika?
Yes.
So wavefront are the locus of points which are vibrating in same wavelength. Just note it down. So when we do Heinz principle, we says that light waves propagate in the form of wavefront. So if you take a source of light in a dark room, then you can say that source of light will generate first wavefront. That wavefront will generate another wavefront, and so on. This is how your light waves can propagate to it.
Sir,
Yes, Arpit.
sir, why is this like different, very confined? Like, why does it not travel all along the water?
This is traveling. Like I have drawn this basically snapshot shows four wavefront, but it travels along the surface of water. And you will have wavefronts here, wavefronts here, wavefronts here. But what happens is when this wavefront travels, it loses energy. Due to loss of energy, its size, like due to loss of energy, after a certain time, you won't experience any vibration.
Okay.
But if there
So,
is no
like, they
loss of
also
energy,
depend upon the mass of the disturbance object, like, just
it
causing.
depends upon the medium, yes. Omar, locus is a term of mathematics. Locus means a curve which follows certain conditions. Here, the condition is all points on the curve are at a fixed distance from the source. If all points on the curve are at a fixed distance from the source, then you call that as the locus. No need to draw this thing, like no need to draw this picture. I just keep this picture for the reference purpose. Write this definition. So Anshika, can you explain what is a wavefront exactly?
So like it is a continuous point जहाँ से
Continuous points which are at a fixed distance from the source. See, just wait 1 minute. Instead of water wave, if I take example of light wave, say consider a dark room. You take a light source here in the dark room. That light source will generate first wavefront. That wavefront will generate next wavefront. That will generate next wavefront. And this is how light spread in a room. So you can assume the light is spreading in the form of wavefront. The source generate first, then the first wavefront will generate the second one, then the third one, and so on. So this is light waves are traveling in the form of wavefront. That was the Heinz theory. If you, in one line, if you want to explain the Heinz principle, this is what Heinz says.
Sir, but in the like case of light, we cannot experience the waveform.
We cannot.
Experience the waveform, like they are not visually visible.
Okay. Yeah. Yes, everyone have written.
1 minute, sir.
Yes, written. See, this Heinz principle is a very theoretical topic. There's no numericals from this section, only some geometrical constructions and few derivations. Derivations are also very geometrical. So there's no formula, no numerical, nothing. It's okay. Yes, written, everyone?
Yes, sir.
It's okay. The next is the type of wavefront, shape of wavefront, basically. Depending upon the shape of the source, your wavefront can have many shapes. Like if you take your source to be a point source. So for this point source, if you take all points at same separation from the point source and you join those points, then you will get the shape like a sphere. So if you have a point source, your wavefront will be spherical wave. So for a point source, you have a spherical wavefront. So this is your point source. And these are the wavefront. This is the first wavefront. This is the second wavefront. And rays are going perpendicular to it. So for a point source, your wavefront is spherical. After point source, and these are rays, and these are spherical wavefronts. But instead of a point source, if I take a line source, like you take light source, you take a tube light. Tube light is like a light source. So if you take a tube light, which is a line source, and you take points at equal separation from the tube light, then you will not get a sphere. Can you guess which shape you will get if you take points equal separation from a line source? Like if I take this line and I ask you to draw a shape by taking points at equal separation from this line, what shape you will get?
Cylindrical.
Cylindrical. So if you have a line source, then your wavefront will be cylindrical. This is a line. You take points at equal separation from the cylinder, equal separation from this line source. So when you join all these points, the shape that you get is a cylindrical shape. So for a cylindrical wavefront, for a line source, your wavefront will be cylindrical. Now, let's say you have a spherical wavefront and your observer is at a very far distance, like your observer is at some 10 kilometer, 20 kilometer. Then the size of the wavefront will be very large. Like, see, you can check from here also, spherical wavefront. When the spherical wavefront as it travels, its size increases. So if your observer is a very, very far point, that means the radius of the spherical wavefront would be very large. An observer will not be able to see the complete wavefront. He will just see a section of the wavefront. And that section of wavefront will appear as plane. The best example is Earth. You know, the Earth is spherical. But when you go outside your home and you look at the piece of land, it appears to be plane. It's not actually plane. Basically, it's a sphere of a very large curvature. You are just looking at a small part of it. The same is here. If you have a spherical wavefront and your observer is at a very, very far distance, when you observe the spherical wavefront, he cannot observe the complete wavefront. He will observe a section of the wavefront, and that particular section of the wavefront will appear as plane. In the same way, if you have a cylindrical wavefront and your observer is at a very, very large distance from the cylindrical wavefront, when you observe this wavefront, it appears as plane. So a small portion of a spherical wavefront or a cylindrical wavefront will appear as plane wave. Okay, do you remember something from ray optics? If your object is at infinity, how the waves will look like, rays will look like? Your object is at infinity, how the rays will look like? Noah? How the rays behave if your object is placed at infinity? Noah? Unib?
They converge at the focus.
Nah. I'm saying your object is at infinity. What is the pattern of rays? Noah is not in class that week,
Sir,
huh?
parallel lines.
Parallel rays. If your object is at infinity, that means rays coming to you will appear as parallel. So the concept of parallel rays, when you use this concept in wavefront, then we call as the wavefront is plane. So parallel rays of ray optics and plane wavefront of wave optics are same thing. So when you say that your object is at infinity and I ask you what is the pattern of the rays, you will say that rays are parallel. And I ask you what is the shape of the wavefront. If your object is at infinity, then the shape would be not spherical, the shape would be plane. Plane wavefront, you will observe. So this is, so if you have a plane wavefront, the rays are parallel. So this is the plane wavefront. If you draw normal, then you will see that you will get rays which are all parallel. So for a distant source means source which is at a very large distance, a portion of spherical or cylindrical wavefront appears to be. Note it down, the shape of the wave. Is it clear, Ishma, Anshika,
Yes, sir.
Minashi? You have doubts here?
No, sir. Clear.
Umar, no, we have not yet finished ray optics. We just have started optics. We'll first do wave optics, then we'll do ray optics. This topic is very scoring. It's a very scoring topic. Can I scroll it now? Umar, Saifullah, Ishma.
Yes, sir.
Just tell. See, these arrows always represent rays. Huh? Rays are perpendicular to wavefront. So these arrows here are representing the rays. Yeah. Can I scroll it? So remember, there is no source which produce plane wavefront. Sources produce either the spherical wavefront or the cylindrical wavefront. But if your observer is at a very, very large distance from the source, then he will observe a portion of the spherical or the cylindrical wavefront, and that portion appears as plane. That's the concept of plane wavefront. Tell me once you have written interrupt. Haji, can I scroll? Okay. Okay, after this plane wavefront, we have converging and diverging wavefronts. So before starting this converging and diverging wavefront, let's first discuss what are converging rays. So Cephala, what type of ray are these? Are these rays converging or these are the diverging rays? Converging rays. Converging rays means they are meeting at a point. And what about these rays, Unil?
So diverging.
Diverging rays. So just like your converging rays and diverging rays, we have converging wavefront as well as the diverging wavefront. So these are the shapes. So if I'm drawing a wavefront in this way, this wavefront, then this wavefront, then this wavefront, then this wavefront, this one, this is the converging wavefront. Okay, if I have a wavefront, how will you draw a ray? If you have a wavefront, Arpit, how will you draw a ray?
Where it is
Using a wave-
perpendicular to the
Perpendicular. So if I plot perpendicular on the wavefront, then these are the rays. And you will see that these rays are perpendicular to wavefront. These are the rays. So you have converging wavefront and corresponding rays are also converging. And this is your diverging wavefront. And if you draw waves, the rays are also diverging. Draw these shapes also. So you have to remember these shapes like spherical wavefront for a point source, cylindrical wavefront for a line source, plane wavefront for a distant source, then converging and diverging wavefront you need. Haji, can I scroll it? Eve, Noha, have you written up to here? It's converging and diverging wavefronts.
Yes, sir.
Yes.
Okay. The next is Heinz construction. See, now Heinz construction is basically the method through which Heinz explained how does a wavefront propagate. Like if I take a point source, like the dark room, I take a point source of light. When I switch on the light source, what happens? Light source will generate one wavefront. Then that first wavefront will generate another. So Heinz principles will explain how the first wavefront can generate the next wavefront. That is basically the Heinz principle. So Heinz says that the first source that you have, this source will generate a wavefront. This is the wavefront, and he called this wavefront as the primary wavefront. This is the primary wave. And you can say this is the wavefront at t equal to 0. So that means this is the position of your light wave at t equal to 0. After a certain instant of time, your light wave will propagate further. So to explain how this wavefront will travel, we use this Heinz principle. So Heinz principles in the first step says source will generate a primary wavefront. You generated a primary wavefront. The shape of the primary wavefront will depend upon the shape of the source. If you have a point source, then your primary wavefront is spherical. If I have a line source, Anshika, then what will be the shape of the wavefront? Anshika, if I have a line source, then what will be the shape of the wavefront? Mehraj, if I have a line source, what would be the shape of the wavefront?
Cylindrical.
Cylindrical, right? If you have a line source, then it will be a cylindrical wavefront. So you have a point source, your wavefront is spherical. So this is the spherical wavefront, first spherical wavefront. See, I'm not drawing the complete wavefront. I'm just showing that light waves are traveling in the forward direction. So I'm not drawing the backward wavefront. No. So first point says source will generate a primary wavefront. The shape will depend upon the shape of the source. Then Heinz says each point on this primary wavefront will behave like a fresh source of disturbance, which simply means each and every point on this wavefront is behaving like a fresh source. So you can put infinite points on the primary wavefront. So all these infinite points will behave like infinite sources. And each source will generate a wavelet. So source will behave, each point will behave like a source. And each source will generate disturbances. We call these disturbances as wavelets. The radius of the wavelets is speed of light multiplied by the time. This is the radius of the wavelet, speed of light multiplied by the time. That's the radius. So this t equal to 0 is the position of your first primary wavefront. Then after certain time t, this wavefront travels in the forward direction. The speed of light is c, so the radius of the wavelet will be ct. So first point is source will generate primary wavefront. Second point is each point on the primary wavefront will behave like a fresh source. Third point is each source, this source on the wavefront, will generate further disturbances. These disturbances are known as wavelets. If you want to calculate the radius of the wavelets, distance is speed multiplied by time. So the radius is speed of light multiplied by time. That ct is the radius. Then if you can draw a tangent over all these wavelets, this is wavelets, this is first wavelet, this is second wavelet, and infinite number of wavelets. If you draw a tangent surface touching all these wavelets, then you get a secondary wavelet. Or you can say this is the position of your light wave after time t. So your light wave have traveled a distance t. So earlier your wave was here. After time t, your wave is here. So I'm repeating again. The first step, source will generate a primary wavefront. Every point on the primary wavefront will act as a fresh source. It generates secondary wavelets. The radius of the wavelets is ct. If you draw a tangent surface on the wavelets, you get secondary wavefront. And this secondary wavefront is the position where your light wave is now. Is it clear? Noha, Hishma, Minashi, Anshika.
Yes, sir.
Yes, sir.
Okay, just write down. This is the Heinz construction or Heinz principle. Look it up. हाँ जी, written. Can I scroll it further if you have written up to here? Saifullah, Umar, Minashi.
Yes, sir.
Saifullah, you are written up to here, point 3.
No, sir. Yes, sir. Done.
Okay, now draw this one. Saifullah, Minashi, Miraj. Is there any declaration from the CBSE about your final exams? Are they in mid-Feb like India or is in March? Is there information from CBSE?
It's in February 15th.
February 15th? Yes, it's, in India it's from February 15th. What about these Middle Eastern countries?
So the official date sheet is released.
And the official date sheet is not yet released. It's just the tentative date, mid-Feb. Is there any official announcement from your school side about the final date sheet of final exam? Is it in mid-Feb or in mid-March?
So they were saying something about mid-Feb, sir.
Mid-Feb, na? Haji, can I scroll now? You all have written up to here? Muneeb, Miraj,
No, sir. Sir, can you scroll up to the third point? Done, sir.
Okay. The next thing is, when you draw wavefront, see, light energy only travels in the forward direction. It does not travel in the backward direction. So backward wavefronts are not possible. Only the forward wavefronts are possible. So this was a flaw in the Heinz theory. So if you go through the Heinz theory, you can draw tangents in the forward as well as in the backward direction. But if you take tangents in the backward direction, this will mean that light energy is traveling in the backward direction, which does not happen. Light energy does not travels in the backward direction. It always travels in the forward direction. So that backward thing is not possible. So that's why backward wavefront is not possible, because light energy travels in the forward direction. Just note this statement. Usually this is a conceptual question, that was there any flaw in the Heinz theory? The major flaw was this. Yeah, can I scroll it now? Sure. So that was the theory in this chapter. In this Heinz theory, Heinz principle, there's just the Heinz principle and the shape of the wavefront. This is the part of theory. Next, we can come to questions. The questions are usually conceptual questions, don't very good. So the first question says, draw the shape of plane wavefront when it passed through a prism. So you take a prism, you pass a plane wavefront through the prism, and you have to draw the shape of the wavefront when it crossed the prism. Similarly, you take a plane wavefront, you insert it over a convex lens, you have to draw the shape of the wavefront. There are two ways to do this question. One is you can do proper geometrical construction, and another is tricky. Like if you know how your rays, your parallel rays behaves for a prism, for a convex lens, for a concave lens, then you can directly draw how the wavefront will look like. So first of all, I'm doing the complete calculation in the first case, then we will do it directly. So that's the first part. You have a prism, and you're supposed to draw the wavefront for this prism. So I'm doing this. So see, this is the prism. This is the prism. You take a wavefront here, and you have to draw the wavefront when this wavefront passes through the prism. How this wavefront will look like when it passes through the prism. So we'll use Heinz principle. Heinz principle says the wavefront which is given to you is a primary wavefront. Every point on this primary wavefront will behave like a fresh source. So I take 3 points here. So I have 3 sources. Each source will generate wavelets. The radius of the wavelets is speed of light into time. So the wavelets which travels from this, let's call this as point A, let's call this as B, as C. The wavelets which travels from point A will have some speed v1, and in time t it travels a distance v1t, and this is the wavelet. Wavelet should be spherical. I'm not drawing the complete sphere, I'm just drawing an arc. Because if you look at the construction carefully, you don't need the complete sphere, you just need an arc so that you can put a tangent over it. So this is my first wavelet. Then what you can do is you have another point. You again draw the tangent. No, sorry, not tangent, wavelet. Then you have another point C. You again draw the wavelet. The radius of the wavelet will be V2T. Now, let's don't take this point B. Point A and C will be enough. Okay, now can you compare the speed V1 and V2? V1 is the speed of light when it's traveled from point A to the prism and then here. V2 the speed when the light is traveling like this way. Can you compare V1 and V2? Are they equal, or V1 is less than V2, or V1 is greater than V2? It's an open question for all. Haji. Only V1
Sir,
and
can you
V2 are
repeat the
equal.
question, please?
Yeah. There are two wavelets. One is traveling from A through the prism and a very small portion of light wave is passing through the prism. Then there is another wave which is starting from C. It's covering a very large portion into the prism and then it's reaching here. I'm asking about the speed of wave if from point A and point C. Is it same or different? From the wave which is going through point A is having a speed v1. The wave which is starting from point C is going with a speed v2 inside the prism. Which speed will be less and why? Munib.
सर सी वाली कम होगी
क्यों?
सर वो प्रिज्म के बेस से पास कर रही है
Right. Major part of the light waves which are passing through the point C is going through the prism. So his speed will be less as compared to the wave passing through point A. So V2 is less than V1. So obviously the radius of the wavelet passing through C will be less than the wavelet, the radius of wavelet from point A now. So what you can do is you draw two wavelets here. Here radius is large because speed is large. Here radius is small because speed is small. Then you draw a tangent here. So this is your secondary wave. Now, once you have wavefront, you can draw rays also. So how we draw rays if you have wavefront, Noah? This is your primary wavefront and this is your secondary wavefront. How will you draw rays if you have
The
wavefront?
perpendicular.
Perpendicular. So you draw perpendicular over the primary wavefront. So these are your rays. We call these as incident rays. Then we draw perpendicular over the secondary wavefront also. We call these rays in ray optics, we call these rays as deviated rays. So rays deviate when they pass through a prism. So this is one way or the actual way to draw. And the shortcut method is do some cheating. You know that this is your primary wavefront. And you know that when this primary wavefront passes through the prism, it bends. Because from ray optics, we know that when light rays passes through a prism, prism deviated. There's a deviation. So this is the primary wavefront. This is the secondary wavefront. Then just draw a straight line. These are your rays. And then draw these straight lines. These are rays. And just to show that you have taken wavelets, just draw two arcs. That's it. This is how you do practically if you want to complete your exam or your paper on time. This is the actual method. But if you want to complete your paper on time, this question should not take more than 1 minute. So what you will do, you have a prism, you draw a primary wavefront, then you draw your secondary wavefront, draw your rays, then put some arc. Is it clear for everyone? Anshika,
Yes,
Arpit,
sir.
Omar. Is it clear for everyone? The actual method and also the shortcut one. Miraj. हो गया ये लड़का गायब हो जाता है बीच बीच में
Yes, sir. कर लिया.
okay okay so for prism you can draw this diagram and I would prefer if you draw it directly. I don't have that much of time to take a compass and take an arc. Just do it directly. Primary wavefront, incident rays, deviated wavefront, or this is your secondary wavefront, and this is your deviated rays. This radius is B2T, here radius. Right. Tell me once you have written, then we'll do it for convex lens, then concave lens, and finally. Yes, Ishma, have you written it?
No, sir.
Anshika, doubts in it? Can I scroll it now? Anshika, Miraj,
Sir, can you repeat what you said?
sorry. I'm asking, did you finish it? Written? Can I scroll it further?
Yes, sir. Yes, sir.
Okay. See the next thing. The next is you have to decide what happens when a plane wavefront passing through a convex lens. So instead of wavefront, just tell me what happens when a parallel line is passing through a convex lens. Noah, what happens when parallel lines passes through a convex lens? What happens to the line? Rays. Parallel rays passes through the convex lens. Noah, as you know, what happens when parallel rays passes through a convex lens? Noah,
The convergence.
yeah, when parallel rays passes through a convex lens, they converge. So the same thing you can apply for the wavefront also. So what happens, Minashi, when plane wavefront passes through a convex lens? What happens to the plane wavefront?
So they converges.
Yeah, plane wavefront converges. So this plane wavefront gets converted into converging wavefront. So this is the plane wavefront, this one, and this is the converging wavefront. So it's again, if you want to do it directly, it's very easy. This is a convex lens. This is your plane wavefront. When it passes through, it will converge. This is the converging wavefront. And just to show that you are actually drawing the wavelets, just draw these arcs. That's it. Just draw these arcs that you are actually drawing the wavelets. Do it. Is it clear how I draw this thing? Because from basic ray optics, I know when parallel rays passes through a convex lens, they converge. So I just take that concept. This is the plane wavefront. This is the converging wavefront, and I draw the rays and the arcs. Arpit, what does these arcs represent? These two arcs? Arpit, what
Sir,
does the yes,
which arc, sir?
this arc and this arc? Hishma, what does these two arcs represent?
So wavelets.
Wavelets. These arcs are for wavelets. Okay, Arpit?
Yes.
These are waves. So ideally, we should first draw the wavelets and then we'll take a tangent. Then you will get the secondary wavefront, but that will take too much of time. So what you can do is you can first draw the secondary wavefront and then you can just draw the wavelets. These arcs are representing wavelets. Can I scroll it now? Next, similarly, instead of convex lens, if I take a concave lens, then concave lens will not converge. Concave lens actually diverge. And this is the shape of your diverging wave. So now you can guess, if you have a concave lens, when they pass through the concave lens, it will diverge. So this is the diverging wavefront, your secondary wavefront, and this is the primary wave. So this is the primary wave. And this is the secondary wave. And what are these lines, Jasola? These arcs, what does these arcs represent here?
Wavefronts.
Wave, not wavefront. Wavefront is this. I'm asking about this arc, Jasola. These arcs are representing wavelets, these wavelets. Okay?
Oh, yeah.
Wavelets they are represented. Do it. Then we'll do mirror.
सर सेकेंडरी वेवफ्रंट क्या है?
जब ये प्राइमरी वेव फ्रंट जब यहाँ पहुंचेगा तो इसको सेकेंडरी कहेंगे.
ओके सर.
जैसे ये रिफ्रैक्टेड रेज है, इसको आप सेकेंडरी रिफ्रैक्टेड रेज कह सकते हैं. इसीलिए प्राइमरी वेव फ्रंट, ये सेकेंडरी. यही आपको डिसाइड करना है कि जब ये वेव फ्रंट इस लेंस से बाहर आता है तो ये कैसा हो जाता है. लेंस से आने के बाद ये शेप में आ जाएगा. दैट इज योर सेकेंडरी वेव फ्रंट. आप इसे रिफ्रैक्टेड वेव फ्रंट कह दो. दैट्स इट.
सर कॉनकेव मिरर कॉन्वेक्स मिरर का भी है क्या?
हाँ जी. कैन आई स्क्रॉल इट इफ यू हैव रिटन अप टू हियर? The next is concave mirror. Miraj, what does concave mirror do? Concave mirror is converging or it's diverging?
Is diverging.
Okay. Safula, concave mirror is converging or diverging? Noah, is concave mirror converging or diverging? Noah, sir.
Sir, mirror.
Converging.
converging. Concave mirror is converging. It's concave lens which is diverging. So if you have a concave mirror and you took one primary wavefront AB, let me draw it again. So this is your concave mirror, and this is your primary wavefront. This is your primary wavefront AB. And concave mirror converge. So this will be your converging wavefront. This is your converging. So this one is your secondary wavefront. And this one is your primary wave. In primary wavefront, along with wavefront, you need rays also. So what you can do is just draw normal. So these white rays that I'm drawing are the incident rays. You can say these are your incident rays. For secondary wavefront, or you can call this as the reflected wave. So to draw the reflected rays, what you can do is you can draw normal on this. So you can draw normal on this wavefront. So this is the normal on wavefront. So this is the normal on wavefront. So these red lines are representing your reflected rays. Now you have to show wavelets also. So just put these arcs here. These green arcs are representing your wavelets. So these green arcs are wavelets. Note it down. Then we'll do convex mirror.
सर ये दो कॉन्केव मिरर बनाए
नहीं, एक concave mirror. This is the concave mirror, and this is your reflected wavefront. This is a mirror.
यस सर और फिर वो दूसरा वाला क्या है जो
पढ़िए जरा क्या लिखा है.
सर सेकंड
Sorry, covered over. Sorry. This is not the converging wavefront. This is the diverging wave. Sorry. Give me 1 minute. Give me one. This is the diverging wavefront, not the converging. The shape of converging wavefront is this. This is the converging. So this will be your wavefront, and these are your rays. See, we draw them earlier also. This is converging and this is diverging. So these are converging rays. This is converging rays. See, this wavefront is coming from this side. So if you compare it from here, the wavefront is coming from here. The wavefront is coming from this side. Now the wavefront is coming from this side. That's why the shape is a bit different. Coming from this side. So if you take this as converging, this will come to the left. Right, sorry, this will come to the right. That's why it looks like. And then using the green one, you can put wavelets also. These all are wavelets. Please draw it. Yes, written. Can I scroll it now? Minashi, Saifullah.
One minute, sir. Yes, sir, done.
The next is the convex mirror. For convex mirror is a diverging mirror. For convex mirror, your wavefront will be diverging. This is the diverging wave. So that's your plane wavefront. These are your incident rays. This is your diverging wavefront. This one, or you can call it as secondary wavefront. And these are your rays. These are your rays. Reflected rays. This is reflected. Right. Only what does this green arc represents here?
Sir, wavelets.
And what the radius of the wavelets?
Sir, CTs. Speed.